Geometric packing problems play an important role, both in theory and practice. Particularly interesting cases arise from packing a set of objects into a given container, for example, placing a set of circles into a square or circular box. In the following, we give a survey of computational complexity and tight worst-case bounds. Even basic versions of the problem are NP-hard, so we cannot hope to come up with an efficient algorithm that solves instances to provable optimality. In a 1990 paper, Leung et al. Showed this for deciding whether a set of squares can be packed into a square container. Their approach is based on a reduction of the classic three-partition problem. Given a set of numbers, partition it into triples of equal total size. The proof shows that the numbers of any three-partition instance can be encoded as squares in a packing instance. These fit into the container if and only if there is a feasible three-partition. A construction for the case of packing circles into a square was given in 2010 by Demain et al. The proof constructs a hierarchy of circles, in which the numbers of three-partition are represented by specific small circles, shown green in this image. Each such triple fits if their total size is not too big, so a feasible packing implies a valid three-partition. The overall result implies that origami design is hard too. A similar proof exists for packing circles into a circle. In addition to these theoretical difficulties, packing circles also has to deal with practical issues of complicated coordinates. As a consequence, heuristics may provide good practical solutions, but provably optimal ones are known only for very small numbers of circles, even when these are identical. Here are the optimal solutions for packing n-unit disks into a unit square. It is not surprising that there are many long-standing, unsolved conjectures in this area. These difficulties make it relevant to establish simple criteria for the feasibility of a packing problem. Can this set of circles be packed into this container? It turns out that we can answer this question simply by considering the resulting packing density, that is, the ratio of areas. For this instance, the packing density is small enough to guarantee a packing, regardless of the particular radii. As we will see, the value 0.5390 is a magic number, the critical packing density. Any set of circles below this threshold can be packed, and for any larger value, unpackable instances exist. This is where other, more involved algorithmic approaches may be needed to decide the existence of a packing. For packing squares into a square, it is easy to see that the critical packing density is at most 1/2. It has been known since 1967 that this is indeed tight, when Moon and Moser gave an algorithmic proof. After sorting the squares according to decreasing size, they pack items greedily into horizontal shelves. If the items cannot be packed in this manner, it follows by relatively simple algebra that their total area exceeds 1/2. The critical density of packing circles into a square was open for many years. In their 2010 paper on circle layout for origami design, Demain, Fekete, and Lang conjectured that this is a worst-case configuration, implying a value of pi divided by 3 plus 2 times square root of 2, or 0.539. In 2017, Moir proved that 0.539 is indeed the critical packing density of circles in a square. Here is a symbolic overview of his split packing algorithm. The idea is to sort the circles by decreasing size. Then split them into two subsets A and B of nearly the same total area, based on a greedy balanced partition. The container is split diagonally into two pieces whose areas correspond to the area distribution of the two subsets. Rounding off the triangle corners yields subcontainer shapes that are called hats, into which we recursively pack the subsets. This recursion is carried out until there is only a single circle in a subset, which is packed into its hat. When the total packing density does not exceed the value of 0.539 from the known worst-case example, we end up with a feasible packing. Here is an example run of the overall algorithm. And here are a number of examples of packings generated by split packing. The idea of split packing can be generalized for other objects and containers. Here are some examples of packing regular octagons or certain types of heptagons called rubies into a square or circles into a triangle. Full details can be found in a recent journal paper. What is the critical packing density of circles in a circle? This example shows that it cannot be larger than 1/2. We use a combination of 4 subroutines to show that any smaller set can always be packed. A recursive call, boundary packing, ring packing, and ring management. The recursion proceeds if the largest 2 disks have radii larger than 0.495 times the size of the container disk, leaving only very little area for the remaining disks. We proceed by placing the 2 large disks and recursively packing the remaining disks into a smaller container disk. The second subroutine is boundary packing. We sort the disks by decreasing radii and iteratively pack them adjacent to the container boundary. We stop when we reach a disk that is smaller than 1/4 of the container, as shown here, or the current red disk no longer fits. The third subroutine is ring packing. Consider a red disk smaller than 1/4 of the container disk. Placing it on the boundary induces a concentric ring. We use this ring for packing like in a circular shelf, alternating between placements near the inner and outer boundary. We stop when a disk is too large to fit, or so small that it can move by the previously packed disk, such as this purple one by the green disk. In that case, the current ring is closed. We place the disk adjacent to the boundary, inducing a new ring to be used in the 4th subroutine, as described next. The final subroutine is ring management. When ring packing stops because of a small violet disk, this disk opens a new ring, highlighted in light gray. The remaining part of the previous ring is also kept as an open ring, highlighted in light gray. If there still is an open ring, we apply ring packing to the open ring with the largest radius. If there is no open ring left, we go back to boundary packing on the indicated light gray area. This leads to a packing pattern in concentric rings, as shown here. The resulting analysis is relatively complex and uses a combination of manual and automated case checking. Proof details are technically involved and can be found in an upcoming paper by Fekete, Keldenich, and Schäfer. And now it's time to pack it up.